It's great to see you. Welcome back to our Distinguished Linguist lecture series. We're actually I'm coming in from Stony Brook University, an actual university today, which is unusual for me, real life. And we are delighted to have Vera with us, who also has a long history with the school. I don't want to actually get the years wrong, but I know you were a student at the school at one point in the very past. And then Vera went off to do her PhD at Rutgers and has been teaching with us. Vera has been teaching with us since, I think, the virtual schools began. She's taught several classes in experimental linguistics and also participated in our AI forum, the beginning of this session. And now we're delighted that she is back to tell us about exploring language processing in voice assistants. And what I think we'll do as usual is welcome you to write any comments or questions in the chat at any time, but leave the primary discussion for the end. Although if you have clarification questions, just as usual, put up your little electronic hand, and we'll turn it over to Vera. So please welcome Vera Gore.
Okay, thank you so much. Oh, is there a question already? Nicole? No? Okay.
No, sorry.
I think it's people saying hi.
Okay, just
using
checking.
the hand to say automatic hand.
Sorry
just
about
that.
Okay, cool. So I will start by sharing my slides. Okay, just 1 second, and you guys let me know if all looks well. How's that looking? All good? Can you see my screen? Perfect, perfect. Thank you so much. Okay, so today we'll be talking about the voice assistant technology and the role linguists play in developing and maintaining this technology. And for those of you who maybe took up some of my previous classes here at Virtual NYI, you know that I like to start with like the very basics, the very simple things. So we hear AI all the time. Like this past year, there was this explosion of technology that came with generative AI and large language models. So what is AI? It is used in many different contexts, and sometimes it's just confusing what the term refers to. So on the one hand, we should distinguish like two major domains, two major interpretations of this term, right? So on the one hand, artificial intelligence is a branch of computer science. And this branch of computer science deals with developing, building smart machines that should be capable of doing tasks that are normally assumed to be tasks that only human beings are capable of, right? So logic, reasoning, question answering, so on and so forth, right? On the other hand, AI, the term itself, is also used to refer to the resulting technology. So not the domain, like the area of science, but the technology that is the output of this scientific area. So it's the capability of computer system to behave in ways that are similar to human ways of behavior. So mimicking human cognitive functions such as learning, such as problem solving, and so on and so forth. So AI could be area of science, could be the resulting technology, right? So in its own turn, when we talk about machine learning, we could also think about it in two different ways. So on the one hand, we can think of machine learning as a subfield of artificial intelligence, like science-wise. It is also a research area where we focus on how machines can execute such complex tasks as reasoning, problem solving, knowledge representation, machine perception, computer vision, so on and so forth. So this is machine learning as a research domain. And technology-wise, we would be talking about using machine learning as a tool to facilitate algorithms to perform mathematical optimization, automated reasoning, probabilistic methods, and so on and so forth. So it is one of the tools that allows computers to eventually behave like humans and perform tasks in human-like manner. So if we think about very standard procedure strategy that any machine learning system would follow, so we would have to go through the following steps. So this is just like a very basic overview before we start talking about voice assistant technology itself. So during machine learning, the first thing that you always have to do is obtain data on which your model will be learning, will be training, right? So that can be text data, visual information, videos, any modality would work here. I will give you some example in a little bit, but you start with some data set. You have to have that. Then what you need to do is somehow pre-process, prepare, or annotate this data. So the model not only learns by looking at the data set, but looking at some additional information that comes with the data set. So for example, it can be text plus transcription, if we're talking about linguistic data, or it could be audio file plus the text that is pronounced in that audio file. So one of that would be an annotated version of the other. Then we choose or create our model, machine learning model. So it is important to choose a model that is relevant to a particular task in hand. And over the years, well, scientists and engineers developed various models suited for diverse tasks like speech recognition, image recognition, prediction, so on and so forth. You need to make sure, for example, that your model is suited for numerical or categorical data. Choose accordingly. So depending on the data type, data modality, you can also make this choice in an informed manner. Once you have decided on that, your next step would be training that model. So basically showing it your data set, your annotated data set, so that during this learning, the model can find the patterns in this data on its own without being necessarily explicitly programmed. And by identifying these patterns, further make predictions using these patterns. So this results in the model learning from the data so that it can accomplish the task that it has in hand. After that, we want to evaluate how the model performs, right? It outputs something, it makes some predictions, and we want to say how good those are. So this is the next step where you look at the model prediction and you look at how human would answer the same question, right? What the model said versus what human has said. You compare that with a human baseline, you see how well you are doing, and you can evaluate your model performance. Parameter tuning comes next, and typically, like when you're developing a tool, you have some parameters. When you're developing a model, you have some parameters you can play with. So for example, if you develop a tool that extracts keywords from a given text, right? The goal is to identify the most important and meaningful words in a paragraph, something like that. So one important parameter there would be something like relevance threshold. So a parameter like that would determine the criteria for selecting keywords. How like high relevance threshold may result in fewer but more significant keywords being extracted and less coverage, right? So you will have fewer items. Lower relevance threshold would mean like more keywords, but potentially less important, less relevant ones. So you will be tuning your parameter and experimenting to see like which threshold results in higher evaluation scores. So this is kind of an example of how parameter tuning would work. And finally, making predictions. So this is where you put your model to work. So all of these steps, as you see, we can see like data, and then like training the model, using the data, evaluating the data that the model outputs. At each point, each step of this way, we are dealing with data. And if we are talking about voice assistant technology, a vast amount of data that you are dealing with throughout this process is language data. And as a result, it requires a linguist to support all these stages and monitor quality, performance quality during machine learning. So Voice assistant technology, here we are. Of course, like all of us as of this moment use digital assistants and voice assistants on a daily basis. So there is no surprise, there is no miracle about this technology anymore, even though like 20 years ago, we were probably only seeing it, like mostly seeing it in movies. But right now, this is an everyday assistant technology that allows us to interact with any devices that we have or applications on our devices using spoken language. So we ask our, computers, phones, our, smart watches, and so on and so forth, and they respond to us either using voice or just by performing actions that we have asked them to perform. So, the goal of the voice assistant technology, very straightforward goal, is to interpret user spoken request and provide appropriate responses. Again, those responses could be worded, they can be language, they formulated as language, or those could be actions. And of course, as a tool, voice assistant technology, it uses artificial intelligence tools, including, as we just mentioned, machine learning and natural language processing. If we go back to kind of your linguistics 101 course, like the very first course that some of you might have taken, just introducing you to how humans perceive speech, let's remind ourselves of some like very basic things. So what happens during, well, before speech perception and during speech perception? The first thing that happens is acoustic wave travels through the air, right? And then your inner ear provides a spectral analysis of that acoustic wave, of this auditory signal. And this spectral analysis is then transferred to our auditory nerve. I would like to kind of mention at this point that, of course, like there are two major language modalities. There's auditory spoken and visual gestural. And while there are systems, incredibly like smart and highly functioning systems of automated speech recognition for sign languages, I will be focusing on the spoken modality today. So what I'm talking about here will mostly focus on auditory spoken modality. So if we just take that acoustic wave, inner ear transforms that into like spectral information and transfers that to the auditory nerve. Neural activity is then transferred to the brain, right? And what happens in the brain is also, like we're well familiar with that, continuous input, right? So all this like spectral information has to be parsed into discrete units. So what we know as phonemes, right? Assigned to like discrete sound representations. And then this string of phonemes needs to be further parsed into morphemes and words. Then the brain assigns structure to those morphemes and words, so identify structural relationships between them. Assign meaning to structure, right? So it's not just the syntactic relationships or more morphological relationships we are talking about. So semantics arrives and assigns, well, is charged with assigning meaning to that syntactic structure. Then the next step, identifying the intent of the utterance and responding appropriately, right? So depending on what the intent is, here comes the domain of pragmatics. When you ask somebody at the table, can you reach the salt, right? You're not just expecting a yes or no question, right? You want the person to actually give this, take the salt and give it to you. So that's the intent of actually requesting for somebody to pass the salt. But when, I don't know, a PE teacher asks you at a physical education class, can you reach your toes? It's not like they want you to take your toes and pass those on to the teacher, but they actually want a demonstration of you touching the toes. So depending on the domain, depending on the context, the intent, even though all the preceding information is the same, might be different and requires a different response. So why am I telling you all of this basic stuff? Because as we said, AI, the general idea, like a basic idea, is for the machine to mimic human behavior in complex tasks. And so what we will be talking about today is how AI resolves the same task, right? So the voice assistant, in a very similar way to process your request, to recognize your request and respond appropriately, it needs to recognize, first of all, that you are addressing the voice assistant, not somebody else in the room, another person who lives with you, right? Or a person, I don't know, next to you in the street when you're talking to your phone. So it needs to recognize that you are addressing it and become activated. Then, the same way, similar to the human brain, it needs to receive the auditory input, same acoustic wave, and then transform that information into a sequence of phonemes, into words eventually. So, right, break this string of phonemes into individual words. Then there might be some differences. So the voice assistant does not necessarily assign syntactic structure to those words, but within those words, it does need to identify meaningful units and predict the intent. Why did you ask this? Like, why did you make this request in the first place? Like, what were you aiming for? What do you want to get? And respond appropriately. So all of these, well, most of these steps do in fact mimic how brain processes language. And let's follow this step by step and see how machine learning algorithms in voice assistant technology deliver you the answer. So when they do the response, again, we said it could be performing an action or providing the information. And as it does so, it can activate the domain that is responsible for this, like action or answer delivery system. It converts the info. So, for example, you're asking a question and there are some documents where the information those documents have the information that could be used as answer to your question. So it needs to extract these documents, extract relevant information, and turn this information into a well-formulated, well-rounded response to your question, and then pretty much read it out to you as the user, right? So this is the output part. So let's trace that step by step and see how linguistic information is relevant, or how linguistic knowledge becomes relevant at each specific step. Remember where we started from. So the first thing, you need to activate your voice assistant. So this is like the very first task that your assistant needs to perform, is to wake up at the moment when it's needed and not wake up at the moment when you want it to remain asleep, right? So it needs to detect this very short word or a short phrase that's intended just for it and nothing else. So the terminology may differ here. It could be like a hot word, trigger word, keyword, wake word. So things, and I guess I apologize in advance if I trigger a bunch of your devices now, but when we say things like, okay, Google, hey, Siri, Alexa, hey, oh yes, and I just activated 2 of my devices, but
okay,
yeah,
I found
exactly.
this on
the so you see how it works. They all woke up. So why do we need that? Why do we need that? Voice assistant, like wake word technology of the voice assistant, is a very small footprint software that has to fit on your embedded device. And crucially, like the whole idea is to, for this short word or phrase, is to enable command detection, but also maintain user privacy. So until you have woken it up, none of your information is being sent to the server. None of your information is being recorded. Your device is just alert for this very phrase. And all the processing and sharing of the information between the device and the server only happens following the activation. So you kind of like, once you activate it, you allow for your following request to be the trigger and well, to be recorded and sent to the server so that your request can be resolved. Right? So until that, your device only listens to you and is out of touch with the outside world. So what makes a good wake word? And this is really, it sounds like a small thing. It's a one word or maybe like a two-word thing. But for any company or any brand, it's a huge decision. And it's something that requires sometimes like several hundreds of people within one organization to work on this one word, like the development, the branding, and so on and so forth. So on the one hand, the wake word should be long enough to be detected with ease by the system. Detecting short phrases is difficult for like both humans and machines, especially in the presence of noise or echo, like if we're talking outside maybe, and there is like some transport passing by. So most well-known wake words have at least 6 phonemes. So like Google has 8 phonemes and 4 syllables, and Alexa has 6 phonemes and 3 syllables. So choosing a wake word with like fewer than 6 phonemes is typically not recommended because it's harder to detect and more likely to produce false positives. Okay, it keeps talking to me. So a short word can be, sorry, it keeps talking to me. I'm just going to turn it off. I knew I would trigger it accidentally. So a short wake word is also a bad idea. Because well, too long is difficult to process, too short is difficult to perceive and difficult to detect. When, for example, your company brand is a short word and you want to make it larger, right? So just so that you have more phonemes there and the extra syllable. The words like hey and okay actually come in very handy. So these prefixes, on the one hand, give you an extra syllable and a few extra sounds. And on the other hand, they also help you disambiguate. So for example, if I just say, like, I can use the word Google in everyday speech. So I Googled that, I know you can ask Google about it, so on and so forth. So this hey or okay prefix actually gives you a way out of this so that you don't wake up your device when you don't mean to. And only the combo between the two, this is like hey, okay, and then the actual like brand, that becomes your wake word, and that has its own benefits to it. And again, for like in terms of phonetics, in terms of phonology, it's better to have a variety of different sounds in your wake word. So combinations of phonemes that are both like easy to discern by a machine and easy to say by human. So you don't want awkward words that are somehow tricky to pronounce as your wake words. You might want to think about inclusivity, like individuals who stutter may have difficulty with sounds that require quick movements of the tongue and lips. So sounds like p, b, t, d, explosives may be not optimal, but fricatives usually tend to be like easier to detect and less tricky to pronounce across various dialects. So tons of factors go into those choices, including, like, again, dialect and language, like whether some sound combinations are dialect or language universal. If your brand, your company brand, is all around the world, you want to select sounds that are more or less present in the sound systems of different languages. At the same time, you want your brand to be unique enough and something that promotes the brand and company device. And also, the choice of the wake word very often has to contribute to an assistant persona. You might want to think of a digital assistant as an object that helps you with your devices, or with, you know, controlling and operating your devices. Or you might want to think about the assistant that is similar to a human being, like your personal assistant. And choosing the name might also be affected by what the like vision of the assistant is, right? So is it like a computer? Is it a person? Is it something in between? So there are a lot of factors to consider. So once we have woken up, activated our voice assistant, we can now ask it to do something for us. So say we want to ask it something like, what's the weather like today? And this is a spectrogram exactly of that. Like, this is what we do when we talk, right? So this is the sound wave that we send through the air saying, what's the weather like today? Or we can say something like, find me a good Thai restaurant nearby. So map a waveform. So the first thing that the assistant does is mapping a waveform into an appropriate string of words. Like, this is what basically needs to happen. And this is where we come into the domain of automatic speech recognition technology. So this is one of more mature and reliable areas of language processing. So call routing has been around, which does exactly that, has been around for years, right? So when you're on a phone call and it asks you, if you want to say what you want to do, and you say 2 or 3 words, and it recognizes your request and it readdresses you to some specific department, I don't know, check your account balance or talk to a representative, like bank representative, something like that. And it can be solved with extreme accuracy. Well, the trick there is that they only have several tokens in their vocabulary and very limited number of options. And when you have a very limited number of options, it's difficult to decide between them, right? But more complex tasks, again, this is old technology. It's been around a while, like message dictation, generating captions for video and audio files, transcribing news and live discussions, accessibility features that we see all around at the moment. So all of this is ASR, translating sound waves into words. And the interesting thing about it is that ASR system is not a monolithic object, right? So it's not, just going straight from the sound wave to words, but really it consists of 2 parts. So the first part is the acoustic model. So those are 2 distinct models. Then there is a language model, and the output of the language model eventually gives us what we are looking for. And just to give you some idea what each of those segments is responsible for. So the acoustic model takes audio, that is your model input, your input data, and it converts that audio into probabilities over phonemes or alphabet characters. So depending on what transcription system that you use, you may be using, again, like IPA transcription, you may be using actual spelling, but transferring, so turning sound into probabilities over the characters that these sounds might represent. So basically, what acoustic model does is something like this. It translates the sound wave into this continuous string of phonemes, or continuing string of letters if we choose to represent pronunciation using spelling. At this point, so the difficulties that, the technological difficulties that arise could be that the waveform of a given word or phoneme does not necessarily have to be uniform across individuals. So each person has a unique way of speaking, as we already know, and different pitch, different timbre to their voice, slightly different way of enunciating, their own peculiar accent, variations in the way they speak, so on and so forth, right? And the assistant needs to recognize the requests from all the different people, right? And be able to generalize over all of those variations. Even when the waveform is produced by the same individual, it constantly is produced in different ways. So depending on the emotion, we do other things differently from time to time. The volume at which we speak affects the sound wave, right? Tons of other factors like outside noise, background noise, so on and so forth. So for a good acoustic model to be able to recognize all of this, right, and respond in a uniform fashion, it needs to have, on the one hand, enough sensitivity to detect instances of different phonemes, right? So when we say different phonemes, it should be sensitive enough to tell the difference between those, but it should not have too much sensitivity to actually, such that it is not able to generalize broader patterns. So it shouldn't be too sensitive and kind of say that, when you're angry and when you're sad, you're producing different types of models different types of phonemes. So it has to be, trained, but not overtrained. When we think about like how acoustic model, like how we prepare data for that and what kind of data goes into training that. We should also think and kind of keep in mind that it can be language independent or language specific, right? So for example, if your voice assistant, and you know that your voice assistant is always addressed in one and the same language, so the users will always speak English to it. So maybe again, you are developing a digital assistant for a US-based banking system, and people will be calling it, and you wanted to address them in English at all times, and maybe then ask them if they want to switch to a different language, but still prompt them in English. Then it needs to be, your acoustic model should be language specific and only trained on English data. If you want your model to activate and detect what language it's being addressed in, then it has to be language independent and trained on all the language that you expect to be used as input. So in general, like once we have arrived to training and the data side, we trained acoustic models on annotated acoustic data. So those would be sound files, right? So those would be corpora consisting of sound files and their accurate transcriptions. So each item in your training set will be audio, and that audio would have to be coupled with a transcription of that audio. And showing enough of those to your model, it should be able to identify the patterns between the audio and the corresponding phoneme strings, and then learn to produce those accurate transcriptions on its own. So that input, right? So the input into the acoustic model is the audio file. It produces the transcription. And language model is the next step, kind of the add-on technology on top of the acoustic model. So this part actually helps to turn the predicted probability. So remember how we said that acoustic models takes audio and converts it into probability over phonemes or characters of the alphabet. So the language model guides the acoustic model, discarding the predictions that are improbable, given the constraints of the given language or the topic of the discussion. So for example, if we have something like this, so this is again the same phrase, so what's the weather like today, right? And this is very likely to be the highest probability phoneme sequence that the acoustic model might offer to you as the transcription. But then it also could do something, okay, so this is my second best guess, and give you, what's the weather like today? Like, well, it's giving you candidates, right? And top ranking candidate says weather, and the second ranking candidate says leather. And it's up to the language model to decide between the two and say like which one wins at this given point, right? So which one is the most likely given what we know about the language and what we know like about the context. So in this case, the most likely probabilistically plausible combination of the two, between the two, is what's the weather like today, and it would be up to the language model to make this decision. And similarly to the acoustic model, right? So language model, it can be like domain independent or domain specific. So we did say acoustic model could be language independent or language specific. And language model, so here it could be domain independent or domain specific. Domain independent meaning that if your assistant is intended to address all sorts of questions, like for example, Google Assistant, right? So we can, it's intended to address any question about any topic out there. So you want to train that language model for that on all like texts from all domains so that it can cater any request with ease. However, if you want to train a specialized digital assistant, for example, a very specific tool that would, for example, transcribe medical dictations, right? So, the doctors, they typically, like especially when they're in a rush, they record, I don't know, descriptions of operations and cases using like voice recording, and then that needs to be transcribed and put into files. So if you want to train a digital assistant to transcribe medical dictations, in that case, you might want to train a domain-specific language model and only train it using medical texts, like medical textbooks, journals, articles, or maybe like existing transcriptions of dictations and so on and so forth. And again, talking about language model, it's trained on pre-processed text data. So that would be a corpora, like large corpora consisting of, first of all, large volumes of text that are representative of the target domain, from which the model can learn which words are typically met next to one another, right? So do we more often see what's the weather versus what's the leather, right? So these are the kind of patterns that the language model would be looking for. So texts that are representative of the target domain and word co-occurrences within this text. So a language model that is trained from the data that is domain specific is likely to assign higher probabilities to collocations, to word combinations that are often used within that domain. So for example, speaking of medical transcriptions, a patient reported having a bowel in her toenails. That is a transcription from a medical digital assistant, which actually what was said in the dictation, the patient reported having a pull in her toenails. But since the model, again, the model was trained for a specific domain, it was trained on medical data, it assigned higher probability to using a word bowel. So patient reported having a bowel pain or a bowel something, right? So that was a more likely continuation than like having a pull. So that was a mistake by the model caused by training data, well, using training data that was like domain specific. I think there is a question in the chat, but actually I have some glitch here and I cannot open the chat at the moment.
It's some interesting, funny commentary, but I don't think.
Okay, cool. Okay. Yeah. So guys, I'm not sure.
So just to,
but yeah, like if you have a question, don't be shy.
I'll notice it. Yeah, I'll bring it if there is one, but
awesome.
We should get through what you want to get through and then we'll have questions.
Sounds good. Sounds good. Okay. So once we have, turned our sound wave into string of words, right? So we have succeeded that. ASR has done its work. Now we are at the second stage, which is natural language understanding. So, and that is a domain, a segment of its own and a different model that we need to train and we need to tune. So here, let's return to our original example, the weather question, and see what happens with it further, like once we have arrived to the NLU stage. So NLU is a critical component of speech processing, which enables the computer system to understand and interpret the spoken language. So basically, the question is like, why is the user saying that? What do they want? What are they asking for? And the NLU model uses the machine learning algorithms to classify the user intent based on the input text. So input detection, input classification, intent detection, intent classification is what happens at this stage. So it involves analyzing the text, right? So the user request to determine the underlying goal or objective, and then extract the entities, extract the information from that intent that might be helpful or relevant to answering the user question. So the goal, the intent may be something, okay, so I want to book a hotel reservation, or I want to order food, or schedule a meeting, or set an alarm clock. All of those will be intents. And slots or entities will be additional pieces of info, like for the alarm clock, what time do you want to set it for? For the hotel reservation, which city, what dates? For ordering food, which restaurant, which dishes? So intent is what do you want to do? Slots are okay, like what are the details of your request? And identifying those, like this is what's at the core of NLU. So for what's the weather like today, intent will be get weather. That's your intent, get weather forecast. And the slot would be time today. That's explicitly mentioned in your request. And another slot will be location. We don't say that explicitly in the request, but the voice assistant has to assume that if it's implicit, it has to mean the place where you are at the moment. So implicit location is where the user is. If we have a request, something like what flights are available from Pittsburgh to Baltimore on Thursday morning. So in that case, your intent will be get flight information, and the slot will be like from which city you're flying to which city, depart date, depart time, so on and so forth. So you get the idea, right? So this is kind of like extracting those items from the request itself. So the NLU model, natural language understanding model, is trained again on large volumes of annotated text. And this would be a corpus consisting of requests similar to those that you expect your digital assistant to be receiving from the user. And those requests need to be annotated to identify intents and slots, right? So there has to be like pre-processing done there. It also needs to consider different ways of asking the same question. Because if you come to think about it, not every user is going to come up there and say, okay, what's the weather like today, right? We may say, what's the weather like today? And we can say any one of those other things. Each of those questions is intended to, get the weather forecast for right now, right? So first of all, again, the digital assistant has to generalize across all the different ways that the request can be made in. And then within each different way, find those intents and slots to be able to understand exactly what the user is asking for. So Linguist's job here is very often to first design the inventory of intents that the system needs to be equipped to handle. So depending on how broad the domain is, again, do we want to cater for everything? Do we want a specialized system, that is just an assistant in booking flights? So the job here will be to create an ontology of those intents, right? And for each intent, predict what slots can this intent take, depending on the domain and also what the linguistic structure is. So if we think about a verb, which can be intransitive, transitive, ditransitive, so on and so forth, right? For every intent, there may be a certain number of obligatory and optional slots, and we need to have an ontology of those so that we can use this classification to annotate the data set on which the NLU model is going to be trained. So once we have the data set in hand, and once we have this classification of intents and slots that we anticipate, we can design the task for the annotators, human annotators, who will follow these very specific instructions and manually process this data set, identifying the required information and labeling it correctly. Of course, now, in a lot of cases, the labels and slots, the labels for slots and intents can be generated automatically. And in a lot of cases, again, especially with the development of large language models, a lot of things can be automated. Still, human annotators need to do some of the work, especially controlling the quality of the output of the automated system. So kind of editing, quality checking, and so on. But it is indeed difficult manual labor, even though it does not require, heavy lifting, but it is tedious and it requires tons of attention, a lot of attention to detail, decision-making skills, editing skills, writing skills. And typically, so a linguist would be working with a team of annotators, designing a task for them, controlling the quality, and making sure that they have clear instructions and they know exactly like how to address the task in hand. After we have processed, so NLU model has done what it was supposed to do, and the digital assistant finally got the idea of what is it that the user is asking and what are the limiting factors, what are the specifics of the request. We come to the response or the information retrieval step. So at this point, the assistant can either perform some action that you have asked, right? If you asked it to play some music, it's going to put on a song, maybe place a call or send a message, set a reminder or an alarm clock, provide directions, so on and so forth, all those different requests. Crucially, I'm listing those in this kind of sequence, because on the top, there are typically requests that don't necessarily require a voice response, right? So play a music or place a call, you can, the assistant should just do that for you without saying anything necessarily. But when you ask a question, you probably want to receive an answer. So the assistant should say something. So when you say, I don't know, hey, no, I'm not going to trigger things. Hey, assistant, play Kill Bill by SZA. What happens there is that, again, acoustic signal is transformed into a phoneme string. Words are identified, word boundaries are identified, intent, like play some music, is identified as well. The slots are filled. So this is Kill Bill is the name of the song. That's a slot. SZA is the name of the singer. So that's another slot. And then what the assistant does, via application programming interface, API, it reaches out to the music service that provides, the music itself. So it sends the command to the music service, and music service starts playing the requested song, and the assistant uses this audio stream and delivers it back to the user. And we are done, if that's the case, if no speech response is required. However, if the response requires some speech, for example, we are asking, hey, assistant, what's the best Thai restaurant near me? The situation is slightly more complicated because that requires the use of yet another model, information retrieval model. So that information, that model, given the user request, given the question that the user has asked, it goes somewhere where the data is stored, where the documents are, and it finds relevant documents that may contain a good answer to the user question, and ranks those documents saying this document is super likely to have an answer to your question. This is the second best. This is the third best, right? So information retrieval model finds good sources that might contain answers. And this model, again, I always mention, what data is used to training the model on each step of the way. So this model would be trained on huge volumes of question document pairings, right? So a question that a user may ask and the document that contains an answer to that question. So your corpus should consist exactly of such pairings. And it also could be trained on explicit user feedback, right? So for each question document pairing, a user might say, yes, that document did contain a good answer to my question. So the model sees that it's a good source. Or no, this is a bad document, and the model can also be trained on that positive, negative feedback and take that into consideration. So just to illustrate what we're talking about here, if, again, we're looking for a Thai restaurant, the model may come up with this following paragraph, and say that this is the source document that contains the answer to the user question. Of course, it should not read out the entire document to you, right? So we need, as the next step, to identify the parts of this document which actually contains something that can be used as an answer, that can be used to respond to the user. So in this point, so we need the name of the restaurant, the address, and maybe some details to make the answer sound a little more personalized. So when we have done our information retrieval, we located the source document. We now need to take those pieces of information and generate a well-rounded natural language response to the user based on this source document. So information retrieval is just locating that source text. Natural language generation, this is our next step, is extracting information from that source document and formulating that as a well-rounded answer to the user. So this model, again, its own thing, is trained on annotated corpora consisting of triplets of information. So like what I showed you here. So this triplet is the question that the user asked, the source text that contains answers to this question, and elements. So this is the third part within this text that are actually answers that could be used as answers to the user question. So this is our triplet: question, source documents, and answer. So, and as a result, once your NLG does just that, it formulates you a well-rounded sentence. The best Thai restaurant in Atlanta is Nam Thai, located there and there. And here comes the last stage. So we need to take this sentence and we need to read it out to you as the user. So here comes the text-to-speech model, which converts these words into an audio, into a string of sounds that is then delivered to the user just vocally. So text-to-speech, TTS, converts written language into spoken language, generates high-quality audio that sounds natural, that sounds human-like, that sounds that's easy to comprehend. And of course, again, so here we are again on the phonetics phonology side of things. It has to incorporate such parameters as emphasis, where it needs to be correct intonation, pronunciation adjustments to enhance how natural the voice sounds. And in its own turn, so text-to-speech model is trained on text audio pairs, right? So you need to have text, you need to have the audio of that text. And typically the corpus for that would consist of a voice talent recording. So that would, at least a standard technology a few years back. Now we can generate voices without necessarily using humans for that. But if you come to think about those assistants that came to be, 10, 12 years ago. So typically there was a specific person who was recorded at the studio, and they delivered hundreds of hours of recording of different texts, and that voice was then used as the basis for the output of the text-to-speech system. So putting it all together, we can think of a system where data feeds from one model into another, and the output of one model is the input of the next model. So from sound wave into the ASR, right? So acoustic model assigns probabilities over phoneme. Language model tells you which words the sequence of phonemes is most likely translates into. The output of ASR goes into NLU, right? NLU is recognizing what are you asking about? What do you want? The output of NLU goes into information retrieval. It finds good source documents to answer your question, or it delivers an actionable action response to you. The output, if we use the information retrieval, that goes into NLG. It generates a sentence answer, or a few sentences answer to your question. That goes into text-to-speech, which delivers you vocal pronunciation. And this is how you get the answer to your original question. So it's going to be cloudy with occasional rain. So if we're talking about the weather question, it may say something like this. And throughout this process, throughout all of these stages, linguists will provide support at various stages. They make decisions about which data sets are required for training a specific model and evaluating the specific model, what the composition of this data set should be to ensure diversity, exclusion of bias, to ensure that semantic domain is covered, so on and so forth. So depending on the domain, like again, it could be within the domain of phonology, then we need to represent a variety of dialects. It can be within the domain of semantics, then we need to cover a broad range of texts in terms of like topics. Then the linguist job would be like to create and maintain those data sets, either generate them or commission them, collect them from the speakers, purchase this data, find this data somewhere. Then ensure, yes, as I just mentioned, that these data sets are unbiased, that they well represent all the information out there. Create instructions for human raters who generate or annotate the data, oversee the quality of, first of all, the quality of annotation, if that is required in the process, and the quality of the model output as compared to human annotation. Perform quantitative and qualitative analysis that can drive decisions about the model design, the feature design, so on and so forth. And finally, maintain models, identify bugs, patch them, and ensure that throughout this process, the system is supported with a person who knows about the nature of the data in hand. And again, like we're dealing with linguistic data throughout. And I'm gonna stop here. Thank you all so much. And I would be happy to answer your questions now.
Thank you so much. I put my 10-minute warning on.